Hello friends, and welcome to our video lecture on topic S3.2 Functional Groups. Our guiding question: how does the classification of organic molecules help us to predict their properties? Our understandings are here if you want to pause the video and read them. Otherwise, here are our objectives. We're going to define organic chemistry. We're going to talk about different kinds of chemical formulae that we use to represent organic molecules. We're going to look at lots and lots of functional groups in organic compounds. We're going to talk about the nomenclature of some of those organic compounds. And we're also going to classify some compounds as being primary, secondary, or tertiary. So what even is organic chemistry? It is a study of carbon-containing compounds. Carbon is pretty cool. It's got 4 valence electrons. That means that it needs to make 4 bonds in order to fulfill the octet rule. That's a lot of really interesting ways that carbon can bind to other atoms. Originally, we thought that organic molecules could only be made by living things, hence the organism part of organic chemistry. We had this idea of vitalism. We living things had some vital force that allowed us to make these organic compounds, until this guy Friedrich Wöhler came along and accidentally made this molecule, urea, in the lab. Previously, urea had only been made by animals when they made urine. Urea is a compound found in urine. But then Wöhler again accidentally made it in the lab, and that changed organic chemistry completely. We had our new modern organic chemistry definition, the study of carbon-containing compounds as opposed to the study of compounds made by living things. We do still categorize those compounds made by living things as natural compounds, and Wöhler, because of his serendipitous accidental production of urea, is dubbed the father of modern organic chemistry. And we have so many ways to represent our organic molecules. We're going to look at those types of formulae here. The first one is my favorite, the full structural formula. This literally shows us every atom bound to every other atom in the molecule. However, this can take a lot of space on paper to draw, a lot of time to draw, so we have some other options. The first two we have already talked about: molecular formulae and empirical formulae. Molecular formulae tell us the exact number of each type of atom in the molecule. In this molecule, which is ethanoic acid, we have 2 carbons, we have 4 hydrogens, and we have 2 oxygens. The empirical formula is the reduced version of the molecular formula, the lowest whole number ratios of those subscripts. So I can divide 2 and 4 and 2 by 2. That's the greatest common factor. That's going to give me the reduced version of C1H2O1. But of course, in chemistry, we like to draw our ones invisibly. I don't know if that's a word. We're going to go with it. And so CH2O is going to be our best empirical formula. We also have the condensed structural formula, which I like second best to my full structural formula, because it shows me kind of like the shape, the arrangement of the atoms in the molecule. So if I look at my ethanoic acid full structural formula here, the first chunk is a C with 3 H's. And so I'm going to start my condensed structural formula with C and 3 H's. And then the next part I see is C with 2 O's and an H. C with 2 O's and an H. So this is my condensed structural formula, which again, I like a little bit better than molecular because I can envision how the atoms are arranged a little bit better than just from the molecular formula. Last but not least is skeletal, which is pretty fun to draw. So we don't draw any C's and we don't draw most of the H's. So we're going to put together a line segment. This line segment, each endpoint is assumed to be a carbon. So this one carbon right here is this one carbon right here. I'm not going to draw the 3 hydrogens around it. I am going to assume that carbon needs 3 hydrogens to fulfill its octet rule. The other endpoint, this one right here, is this carbon right here. Now, it has some stuff that aren't hydrogens bound to it, so I do need to draw that because it's special and different. So I'm going to draw a double line to an O, and I'm going to draw a single line to OH. So this chunk right here is this chunk right here. And this is this. And then, again, the end point right here is this one carbon right here. And this endpoint is this carbon. And I don't draw the hydrogens because I assume that if I haven't drawn something else, we're going to fulfill those octet rules with hydrogens. All of our organic molecules have lots and lots of carbons. We are going to add to those carbon chains some super cool functional groups. Functional groups are atoms or groups of atoms that give organic compounds their physical and chemical properties. If we know what the functional groups are, we can make predictions about the properties of these molecules. The functional groups also determine the classes of organic compounds that these molecules are in. The first we're going to look at are alkyl groups. These are just carbons and hydrogens. This molecule is composed of only carbons and hydrogens. Its functional groups are solely alkyl groups. And how we name these compounds that have alkyl groups depends on the numbers of carbons, because in organic chemistry and also biochemistry, we really love to count the carbons. So here we have a list of alkanes. Alkanes are molecules with alkyl groups, just carbons and hydrogens, and they're going to have only single bonds between the carbons. We're going to talk about double bonds and triple bonds later. So alkane, notice that A in there tells us single bonds between the carbons. There's one carbon, we're going to call it methane, because our prefix for one is meth. 2 is eth. So if I have 2 carbons, no double bonds, nothing but hydrogens, we have ethane. 3 carbons is propane, 4 is butane. And then the rest of these are more similar to the prefixes that we're used to, pent, hex, hept, oct, non, dec. But these ones are new and different. So make sure that you're practicing meth, eth, prop, bute, meth, eth, prop, bute. We're going to call this group of compounds methane, ethane, propane, butane, and then pentane, hexane, etc., etc. These are known as a homologous series. Homologous series. The only difference from one of these molecules to the next is the addition of a CH2. So we've added a carbon and 2 hydrogens. Here we just had C to H. I am going to insert between that C and that H a CH2 group. Same thing here. I'm going to insert here this CH2. So we're really just lengthening the carbon chain. This super cool idea that carbon can make chains with itself is known as catenation. Catenation, the sequential binding of the same atom over and over and over in a chain. Carbon chains, catenation. These alkanes are going to have what we give a general formula. The general formula for alkanes is CnH2n plus 2. So whatever number of carbons there is in the molecule, we can double it and add 2. We're going to get the number of hydrogens. For example, in propane, we have 1, 2, 3 carbons. So that's C3. The number of hydrogens is going to be 2n plus 2. 2 times 3 is 6. 6 plus 2 is 8. Notice that we do in fact have 1, 2, 3, 4, 5, 6, 7, 8 hydrogens. This general formula works for all of our alkanes. A super cool thing about our homologous series is that they're going to all have similar chemical properties because they have the same kinds of atoms bound in the same ways. They're going to react similarly. These alkanes are all highly combustible, releasing lots of energy when we burn them with oxygen. An interesting thing about their physical properties, like here we have boiling point, is that it is going to gradually change. We have a gradation of these physical properties like boiling point. So notice that the boiling point of methane is crazy low, negative 161 degrees Celsius. Ethane's a little higher. Propane higher yet, butane even higher again. The reason that we have this increase in boiling point is, can you guess? It's an intermolecular force reason. Well, we've got more atoms, which means that we have more electrons, which means that the London dispersion forces are going to increase. These molecules get stickier and stickier, which means that more energy is needed to turn them from a liquid into a gas, because more electrons means more of those instantaneous dipoles. Sometimes we can switch up our alkyl groups that have only carbons and hydrogens by adding some double bonds. We're going to call these double bonded carbons molecules alkenes, which is different from the alkanes that we've been talking about. Alkanes, single bonds. Alkenes, now we throw in some double bonds. We're going to call these guys unsaturated as opposed to the alkanes, which are saturated. Saturated hydrocarbons have as many hydrogens as can possibly fit on the molecule. Here we're going to remove some of the hydrogens by adding a double bond between the carbons. So we used to have 1, 2, 3 hydrogens on this carbon, and we had 2 hydrogens on this one. But when we made a single bond a double bond, we were able to remove those hydrogens and still fulfill that octet rule. Hence the unsaturated, not as full of hydrogens as is possible. So here I have, let's count our carbons. 1, 2, 3, 4 carbons. That's going to give us bute. It has a double bond between the carbons. We're going to give it an ene name. So this is butene. How about this one? I've got 1, 2, 3, 4 carbons. 4 carbons is bute. And it has a double bond, so it's ene. How do I know the difference between these two molecules? Because they're not the same, right? If I have a double bond here, I have a double bond here. Those are different places for double bonds. These molecules are going to be different molecules. I can't give them the same name. Friends, we love our numbers in organic and biochemistry, and so we're going to call this molecule, because the double bond comes right after carbon number 1, we're going to call it but-1-ene. That's right, we throw a number into the middle of our letters. Can you guess what we're going to name this one molecule where the double bond comes right after carbon number 2? Yes, it is but-2-ene. But-1-ene, but-2-ene. We can also call this 2-butene, but sometimes we like to have the numbers as close as possible to the thing that they're describing, which in this case is that double bond on carbon number 2. These two molecules are known as isomers. Isomers are molecules that have equal numbers of each type of atom. We have the same number of carbons, there are 4 of them. We have the same number of hydrogens, there are 8 of them in each of these molecules. So they're equal isomers in terms of the numbers of atoms, but we have put those double bonds into different places. We're going to call these structural isomers. The structures are different, even though their molecular formulae are the same. We have a generalized formulae for our alkenes. That is going to be CnH2n. That's different from our alkanes. Remember that alkanes were CnH2n plus 2. We removed those plus 2's when we added our double bond. The general formula for alkenes, that unsaturated double bond, is going to be CnH2 times n. But wait, there's more. So we can add a double bond to make an unsaturated hydrocarbon. We can also add a triple bond. Alkanes had all single bonds between the carbons. Alkenes have double bonds between the carbons. Alkynes have triple bonds between carbons. Also unsaturated because we're going to remove some hydrogens when we make these triple bonds. Let's name these alkynes. We have 1, 2, 3, 4 carbons. 4 is bute. So this is going to be bute something ine. Should I call it but-3-ine? It's tempting because 1, 2, 3, 4, that triple bond comes after carbon number 3. But here's a super cool thing about molecules. They do not go flat on a piece of paper. They are, in fact, 3-dimensional, spinning around in space. And so there isn't really a left or a right or a top or a bottom. So we always count from the end of the chain that is closest to the super cool thing. And in this molecule, the super cool thing is a triple bond. So I'm not going to number 1, 2, 3, 4. In fact, I'm going to number 1, 2, 3, 4. So now I can see that the triple bond is closest to carbon number 1, but-1-ine. How about this one? Should I number 1, 2, 3, 4, or should I number 1, 2, 3, 4? Well, if I go the left to right direction, the triple bond comes after carbon number 2. That would be but2-ine. But if I count in the right to left number, the triple bond comes after carbon number 2. So it doesn't matter. We can count either way. So this is but2-ine. Carbon number 2 is where that triple bond is going to start. We also have a general formula for our alkynes, our triple bonded alkyl compounds. We're going to use CnH2n minus 2. Our alkanes, CnH2n plus 2. Our alkenes with a double bond, CnH2n the end. And our alkynes, we're going to take 2 away. That triple bond dehydrogenates, removes a lot of hydrogens from these molecules. They are also unsaturated. Here's where things get interesting. We can take these hydrocarbons, these alkane and alkene and alkyne groups, and we can add some branches. So here we have 1, 2, 3, 4, 5 carbons. 5 is going to be pent. This is pentane because it's got those 5 carbons, no double bonds, nothing else. It's just pentane. This guy, I have 1, 2, 3, 4, 5 carbons, but it is in fact not pentane anything because I'm going to count what we call the principal chain or the parent chain, the longest carbon chain that we can find that is continuous. So I could count 1, 2, 3. Here's a continuous chain. I could count 1, 2, 3, 4. Here's a continuous chain. I could count 1, 2, 3, 4. Here's a continuous chain. Our longest continuous chain is going to be 4 carbons. So this is going to be butane. But I have a super cool branch on it. So on my branch, I'm going to call this one my branch this time. So I could count 1, 2, 3, 4, or I could count 1, 2, 3, 4. I want to start counting from the end that's closest to the super cool special thing, which in this case is this. We're going to call it a methyl group because it has 1 carbon in the branch. So this is a methyl group. Should I call it 2-methyl or should I call it 3-methyl? Again, we always start closest to the end. So I'm going to use 2-methyl butane. It is going to be called 2-methyl butane. Because again, I've got a methyl group, a 1 carbon branch on this butane molecule. What about this one? This one also has 1, 2, 3, 4, 5 carbons. However, my longest chain is going to be 1, 2, 3, or 1, 2, 3, or 1, 2, 3. Whichever way I count, I'm going to get 3 carbons in the longest continuous chain. So my parent chain or my principal chain is 1, 2, 3. That's meth, eth, prop. So here I have propane. If I count, I'm going to use left to right because that's how I learned how to read. I'm going to use 1, 2, 3. I have a methyl branch, methyl because it has 1 carbon in it. I also have this methyl branch, methyl because it has 1 carbon in it. So that means that I have 1, 2 methyl groups on carbon number 2. That means that I have a dimethyl. Methyl groups, these branches that have 1 carbon, di because I have 2 branches. What carbon number are both of those branches on? Carbon number 2 is what those branches are on. Both of the branches are on carbon number 2, so are you ready for this magic? We're going to call it 2, 2 dimethyl propane. 2, 2 dimethyl propane. This tells us that on carbon number 2, there's a methyl group, and on carbon number 2, there's a second methyl group. And the longest chain, the principal chain of the parent chain, has 3 carbons, hence prop. 2, 2 dimethyl propane. Are we having fun yet? All right, one more little piece of vocabulary related to these molecules. These are known as isomers. All of them have 5 carbons. All of them have 12 hydrogens. They are isomers. These ones we're going to call chain isomers. They do all have the same molecular formula. That's how they are isomers. But now we're just putting the branches in different places. We are changing the length of the principal or parent chain. Hence, these are chain isomers. Let's go backwards. So now we have the name first. Let's draw it. I'm going to start by looking at this hex. This hex is telling me how many carbons are in my parent or principal chain, that longest carbon chain. Hex is 6. I've got 6 carbons. So I'm going to draw 1, 2, 3, 4, 5, 6. Ein tells me that I have a triple bond, and that triple bond comes after carbon number 2. So 1, 2, 3, 4, 5, 6, triple bond after carbon number 2. What comes next? 4 ethyl. 4 ethyl. 4 tells us carbon number 4. Eth tells us 2 carbons in a branch. Eth is 2 carbons in our branch. So I'm going to find carbon number 4, and I'm going to draw a branch that has 1, 2 carbons. That's all the super cool special stuff. So now I'm going to fill in everything else with single bonds. And if I'm drawing my full structural or displayed formula, I'm going to show all of my hydrogens. So hydrogen, 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 because this carbon needs 4 bonds to get to full octet. This carbon right now has 1, 2, 3, 4 bonds, no hydrogens for it. This carbon has 1, 2, 3, 4 bonds, no extra carbons. Ooh, sorry, no extra hydrogens, no hydrogens on it. How about this one carbon? I've got 1, 2, 3 bonds. It does need a hydrogen to fulfill that octet rule. How about this one? We need 2, and this one needs 1, 2, 3. This carbon has 1, 2 bonds right now. It needs 2 hydrogens. And this sad and lonely hydrogen, carbon, sitting way out here, only has 1 bond, so it's going to need those 1, 2, 3 hydrogens to fulfill that octet rule. And here we have 4 ethyl hex 2 ein. But it's not only branches of carbons and hydrogens that we can add to our carbon chains. We can also create some halogenoalkanes, that's the name of the class of molecule, by adding halogeno functional groups. You probably guessed halogeno groups have halogen atoms in them. So I had this molecule, which was methane, because it's got that 1 carbon, 1, 2, 3, 4 hydrogens, but I chopped off a hydrogen and I replaced it with this super cool chlorine. This guy was called methane. This guy is called chloromethane. Do I need to say 1 chloromethane? I don't, because there's only 1 carbon. Of course, the chlorine is going to have to be on that carbon. So chloromethane is perfect. What about this guy? I've got 1, 2 bromines, only 1 carbon. That means that it is meth again. And I've got 1, 2 bromines. I'm going to call it dibromomethane. Do I have to say carbon number 1? Again, I don't, because there's only 1 carbon, so of course it's going to be on carbon number 1. Dibromomethane. 2 bromines on a 1 carbon molecule. What about this guy? Super cool. So here we have one of our skeletal formulae. Remember that that means that each endpoint is a carbon. So I've got 1, 2, 3, 4 carbons, meth, eth, prop, bute. I've got all single bonds, so I know it's going to be ane at the end. So I've got bromine, and I've got chlorine, and another chlorine. I could count carbon 1, 2, 3, 4, or I could count carbon 1, 2, 3, 4. So it's kind of a tie, right? You're like, well, I have chlorine on carbon number 2, or I have bromine and chlorine on carbon number 2. When we have a tie like this, what do? we alphabetize. And because B comes before C, we're going to talk about bromine first. So I'm going to use carbon 1, 2, 3, 4, because 2 comes before 3 when I'm talking about the bromine. So we're going to get rid of those blue numbers. We're going to keep just the purple ones. So what do I have? I have bromine on carbon number 2. So that's a 2-bromo. I also have chlorine on carbon 2 and another chlorine on carbon number 3. That means that I've got 2,3-dichloro. 2 chlorines, 1, 2. One of them's on carbon number 2 and one of them's on carbon number 3. So which one do I put first? Do I call it 2-bromo, 2,3-dichloro, butane, or do I call it 2,3-dichloro, 2-bromo-butane? We alphabetize. And because, again, B comes before C, we are going to call this molecule, are you ready? 2-bromo, 2,3-dichlorobutane. Good job. Another functional group that we can add to our carbon chains is the hydroxyl group. Hydroxyl groups are OHs. OHs in ionic compounds. That OH minus is hydroxide, right? Here in our organic covalently bonded molecules, it is going to be hydroxyl group. Super similar, just a little bit different. Not an ion, just a functional group. When we add hydroxyl groups to our carbon chains, we produce the class of compound alcohols. So this is an alcohol. How do we name it? Well, always we're going to count our carbons. We have 1, we have 2. 1, 2, our 2 carbon prefix is F, meth F for 2 carbons. When we add the hydroxyl group, we're going to change the name from ethane to ethanol. So our alcohols are going to end in this suffix -ol. Ethanol has 2 carbons, hence the F. -ol tells us that there's a hydroxyl group, the functional group hydroxyl group, on this molecule, and that makes it an alcohol. Here are some more examples of alcohols with their hydroxyl groups. Here's my hydroxyl group. It's going to be on carbon number 1, 2, 3. 3 carbons means prop. That hydroxyl group is going to change propane into propanol. I can say 1-propanol. I could also call this propan-1-ol. Same idea here. I have a hydroxyl group and I have 1, 2, 3 carbons. So this again is prop. And it is again -ol, but now it's 2-propanol or propan-2-ol because my hydroxyl group is on carbon number 2. This one is pretty cool, methyl 2-propanol. So I've got 1, 2, 3 carbons in my parent chain, hence the prop. I have a hydroxyl group on carbon number 2, hence 2-propanol. I also have a methyl group on carbon number 2. I don't actually have to say 2-methylpropan-2-ol because if that methyl group were here instead, it would actually be butanol, not propanol. So we can call it 2-methylpropan-2-ol. We can also just say methyl because of course it's going to have to be on carbon number 2. So these first 2 guys are what we call positional isomers. So once again, they are isomers. They have the same numbers of carbons and hydrogens and oxygens. We're going to call them positional because the only difference between the two is the position of that hydroxyl group, carbon number 1 versus carbon number 2. This guy is not an isomer of the other 2 because it's got a whole extra CH, well, technically CH2. It's got an extra methyl group that makes it not an isomer of these other ones. Not the same molecular formula. We're going to talk about the carbons that the hydroxyl groups are bound to tell us these different levels of alcohol, which is going to be super important when we talk about the reactions of alcohols in a couple lectures. So the hydroxyl group on carbon number 1 here. The carbon that the hydroxyl group is bound to one other carbon. Because the hydroxyl group stuck to the carbon, that carbon is stuck to one other carbon, we're going to call this a primary alcohol. This guy, the hydroxyl group is here. The carbon that the hydroxyl group is bound to is stuck to two carbons. We're going to call this a secondary alcohol. What about this last guy? Pretty cool. This carbon that the hydroxyl group is bound to is stuck to 3 other carbons. That's going to make it a tertiary alcohol. But wait, there's more. Another functional group. This one is the carbonyl group. Carbonyl groups are going to be double bonded oxygens on a carbon. Double bonded oxygens on a carbon. If we have a double bonded oxygen on a carbon that's in the middle of a carbon chain, we've got C, we've got C, we've got C. This guy's not at the end. This is going to be what we call a ketone. If instead we have our double bonded oxygen on what we call the terminal carbon, the carbon that's the end of the carbon chains, now we have what's called an aldehyde. The functional group for both of these is a carbonyl group. The class of compound can be a ketone if the carbonyl group is not at the end of the carbon chain. It's an aldehyde if it is at the end of the carbon chain. To name our ketones, we are going to simply count the number of carbons. 1, 2, 3. That's prop, meth eth prop. And then we're going to name it one at the end. So propanone. This is more commonly known as acetone, but the appropriate IUPAC name is propanone. If we have instead carbon 1, 2, 3, or should we name it carbon 1, 2, 3? That's better because this is the super cool special stuff. This one aldehyde, we're going to name propanal. So propanone, if the double bonded carbon is not at the end of the chain, propanal, when the double bonded oxygen is at the end of the carbon chain, we call that the terminal position. Let's name some more compounds that have carbonyl groups. Here we have our double bonded oxygen. It's super cool and interesting, and so I'm going to count my carbon chain starting closest to super cool fun stuff. Carbon 1, 2, 3, 4, 5. Let's count this one. Here's my double bonded oxygen, super cool fun stuff. I'm going to start counting closest to its end. 1, 2, 3, 4, 5. Double bonded oxygen on this guy doesn't really matter because it's like smack in the middle. So we can count 1, 2, 3, 4, 5. We could have also counted 1, 2, 3, 4, 5. Doesn't even matter. So let's name these. All of them happen to be positional isomers. Remember that positional isomers are molecules that have the same molecular formula, same numbers of carbons and hydrogens and oxygen in this case. We're just changing the position of that double bonded oxygen. These are all positional isomers. So this first guy, because we have our double bonded oxygen, this carbonyl group at the terminal position, the end of the carbon chain, it is an aldehyde. I'm going to call it pentan because of my 1, 2, 3, 4, 5 carbons. The end is going to be al, pentanal. I do not have to say pentan 1-al because if it wasn't on carbon number 1, it wouldn't be al. So pentanal is all we need. If we have our double bonded oxygens, carbonyl groups in the not terminal position, but somewhere in the middle of the carbon chain, we might have to add some numbers. So this guy is on carbon number 2 and this guy is on carbon number 3. Both of these are going to be ketones because we do not have the double bonded oxygen, the carbonyl group at the terminal position, but instead somewhere in the middle of the chain. And so this one on carbon number 2 is going to be pentan 2-one because it's a ketone. And this guy is going to be pentan 3-one. and one more functional group that we need to know how to name. So the functional group is the carboxyl group. The class of organic compound is carboxylic acid. Pretty much we're going to take a carbonyl group and a hydroxyl group and mash them together, hence carboxyl group. Carbonyl plus hydroxyl is going to give us carboxyl group, COOOH, carboxyl group, and then our compounds class will be a carboxylic acid. We are going to count the number of carbons. One carbon. One carbon is our prefix meth, and then I'm going to call it oic acid. So this one is methanoic acid. Oic acid tells us carboxyl group at the end. Let's name this guy. I've got carbon number 1 is always going to be the one in the carboxyl group. Always, always, always. You might be going, oh, but chlorine is pretty interesting too. Doesn't matter. Never matters. The carboxyl group always, always, always gets carbon number 1, 2, 3, 4. So I'm going to call this 2-chloro, carbon 1, carbon 2, carbon 3, carbon 4. What's our prefix for 4? Meth, eth, prop, bute. So this is 2-chlorobutane. Because it's a carboxyl group, it's our carboxylic acid, butanoic acid. Oic acid tells us COOOH. 2-chloro tells us that there's a chlorine group on carbon number 2. So purple guy in this one is iodine. We use purple to represent iodine. Notice here I've got COOOH. Here's my carboxyl group. It always gets carbon number 1, 2, 3. Ooh, I've got a branch. Does it matter if I go 4 or if I go 4? It totally doesn't matter. I'm going to call that one 4, which means that this one is my branch. It has 1 carbon in the branch. That's going to make it a methyl group. So what do I have? I have a carboxyl group. That makes it a carboxylic acid. Because I have 1, 2, 3, 4 carbons, meth, eth, prop, bute, it is going to be eventually butanoic acid. I also have on carbon number 2, iodo. Iodo is my prefix for iodine, 2-iodo. And on carbon number 3, I have a methyl group, so 3-methyl. Should I put iodo or methyl first? I comes before M in the alphabet, and so it is going to start with iodo. So the whole entire name of this crazy big molecule is going to be 2-iodo, 3-methyl, and then again, butanoic acid. 2-iodo, 3-methyl butanoic acid. 2-iodo for the iodine on carbon number 2, 3-methyl for the single carbon branch on carbon number 3, butane because my longest parent chain of carbons is 4 carbons long, oic acid because of that carboxyl group. And I know I just said on that previous slide that that was the one more functional group that we had to be able to name, and here are more functional groups. But we don't have to learn how to name the compounds for IB Chem. We just have to recognize, identify the functional groups. So more to know, but not that much more to know. Alkoxy groups. Alkoxy groups are going to be single bonded oxygens on 2 carbons. So C, single O, single C. This is an alkoxy group. It's going to be a class of compound called an ether. Esters are similar. We have C, single O, single C, but one of those carbons is going to be double bonded to an oxygen. So this one is an ester group. The class of compound is also called the ester. So ester group, ester molecule, alkoxy group, ether molecule. We also have a couple of kinds of functional groups that have nitrogen in them, hence nitrogenous functional groups. We have amido and amino functional groups. amino groups have no double bonded oxygens. So here I have nitrogen that is bonded to a carbon. That carbon is not bonded to any oxygens with double bonds. Amidos, however, do have double bonded oxygens. This nitrogen is bound to a carbon that I know that's really bad grammar, but it's easy to remember, that do have a double O, hence double O amido. This nitrogen is also bonded to a carbon that do have a double O, hence amido. This nitrogen is bonded to carbons with no double O's. This is an amino group. We can classify our amines and amides just like our alcohols into primary, secondary, and tertiary. But I'm not going to count how many carbons are on the carbon. I'm going to count how many carbons are on the nitrogen. This nitrogen is bound to one carbon. It is a primary amine. This nitrogen is bound to two carbons. It's a secondary amine. This nitrogen is bound to 1, 2, 3 carbons. It's a tertiary amine. This nitrogen is bound to one carbon. It's a primary amide. This R means that there's more stuff besides hydrogen stuck to it. So it could be maybe another methyl group or all sorts of other super cool things. And so it's bound to 2 carbons. It's going to be secondary. This nitrogen, notice that it has 2 R groups. R means anything that's not a hydrogen. So it could be a couple more methyl groups or maybe even an ethyl group. We don't even know, but it doesn't matter. We do know that they're not hydrogens. Therefore, this nitrogen is bound to 1, 2, 3 carbons. That makes it a tertiary amide with an amido group bound to 3 things that aren't hydrogens. And this is the final functional group that we need to be able to recognize. We don't have to name it. We just need to identify it. The functional group is called a phenyl group. It is derived from the super cool molecule called benzene. Benzene is C6H6, and it looks like it has single bond, double bond. But in fact, what happens is those single bonds can kind of flip back and forth with the double bonds. So in reality, we kind of have like 1.5 bonds all the way around. So sometimes you'll see these drawn with alternating single doubles, but sometimes you'll see them drawn with a little circle on the inside. Same things. The group is called a phenyl group, and the class of compound is an aromatic, and you can probably guess that it's called an aromatic because it smells nice, or smells bad. It just smells. If we have a molecule that does not have a phenyl group or this aromatic ring, we're going to call it aliphatic. So aliphatic is the opposite of aromatic. Aromatic have phenyl groups, aliphatic molecules do not. This molecule is penicillin, an antibiotic. It's a compound that we steal from fungus. Fungus makes it to ward off bacteria because it doesn't want to have to compete with the bacteria for the detritus that it feeds off of. Penicillin, again, we use it to also kill bacteria. Let's look at some of its functional groups. Notice here, we've got a COOH. That's a carboxyl group. Notice that I have nitrogen bound to a carbon that do have a double bonded oxygen. That makes this an amido. That nitrogen is bound to 1, 2, 3 different carbons. That makes it a tertiary amide. What about this guy? It is also bound to a carbon that has a double O. It do have a double O. That makes it another amide. The nitrogen is bound to 2 carbons and 1 hydrogen. That makes it a secondary amide. This is a super cool ring. Is it a phenyl group? It is not a phenyl group. Here's another interesting ring. We're going to call this a cyclic amide because it's got the amido group in it. But even though it's a ring, it's not a phenyl group. This guy, however, absolutely is a phenyl group. That makes this an aromatic compound. Here is another aromatic compound. Why is it aromatic? It's got a phenyl group. This molecule is phenylalanine. It is one of the amino acids that we use to build proteins. Why do we call amino acids amino acids? Well, looky here. There's an amino group. No, because the amino group is bound to a carbon. This carbon is not bound to a double bonded oxygen. So it's amino, no, double O. What have we got over here? I see a COOH. What group is that one group? It's a carboxyl group. And remember that carboxyl groups make compounds that are called carboxylic acids. So because this is a carboxylic acid and this is an amino group, this is an amino acid. Phenylalanine, phenyl group. One more little bit of practice identifying functional groups. This is muramyl dipeptide. It is a bacterial glycoprotein used in bacteria to build cell walls. Oh, so many functional groups. What is this one? COOH. That's a carboxyl group. What about this one? I see a nitrogen bound to a carbon that do have that double bonded oxygen. This is an amido. What about this nitrogen? Bound to a carbon, double bonded to an oxygen. It's another amido. This amido is bound to only one carbon, two hydrogens. That makes it a primary amido. This nitrogen is bound to one carbon, two carbons, and one hydrogen. Two carbons on that nitrogen makes it a secondary amido group. How about this one, nitrogen? Amino or amido? Oh yeah, there's another double bonded oxygen. It's another amido, and it is once again secondary. What about this one, nitrogen? Oh yeah, once again, amido. Is this a phenyl group? It is not a phenyl group because there's an oxygen here, not a carbon. So this is not a phenyl group. This is just a ring. This is not aromatic. Remember the word that means not aromatic? Aliphatic. This ring that is not a phenyl ring does have an OH and another OH. What are those groups called? Hydroxyl groups. And what about this one? Is it a carboxyl? I've got a C, I've got an OH. It is not carboxyl because there's no double O over here. It is simply hydroxyl one more time. And just a quick little talk about these guys that kind of go this way and then go that way. We draw our molecules on a flat screen or a flat piece of paper, but in reality, the molecule is quite three-dimensional. And so this is showing that this part of the molecule comes up toward us. And this is showing that the molecule goes back away into the screen, away from us. And friends, we did a lot of work in these minutes. We accomplished talking about classification of organic molecules. We looked at all of these objectives. We defined organic chemistry. We distinguished amongst the different types of chemical formulae. We had our full structural, we have our skeletal, we have our condensed structural. We talked about identification of lots and lots of different functional groups, our hydroxyl groups, our carboxyl groups, carbonyl groups. We talked about nomenclature for lots of organic compounds. How do we name alkenes and alkynes? How do we name the alcohols and the carboxylic acids? We also classified our nitrogenous compounds and our alcohols as being primary, secondary, and tertiary. Well done.